You know what I find genuinely strange? Not black holes, not quantum mechanics, not the fact that time slows down when you move fast, though all of that is strange enough. What I find genuinely strange is the word broken. People say it all the time, break the laws of physics, as if somewhere out there there's a courthouse, and in that courthouse there are rules written on stone tablets. And if you're clever enough, or if you want something badly enough, you can sneak around back and find a loophole. Scientists in movies do it. Superheroes do it. Occasionally, people on the internet claim to have done it in their garage with some magnets and a dream. And the reason this bothers me, really genuinely bothers me, in the middle of the night, is not that people are wrong. It's that the question underneath the question is so much more interesting than the answer they're reaching for. So let me try to explain this the way I'd explain it to myself, starting from the beginning, which means starting from something you already know. You've dropped something. A cup, a phone, a child's toy off a table. You know what happens. It falls. You didn't calculate it. You didn't reference a manual. You just knew. And that knowing, that deep, unremarkable certainty that the thing is going to fall, that is the closest thing to a law of physics that your body has ever felt directly. Now here's where I want to flip this on you. Gently but firmly. You probably think the cup fell because gravity told it to. Because there's a rule, a law that says things fall, and the cup had no choice but to obey. This is a completely sensible way to think about it. It matches every experience you've ever had, and it is in a very precise and specific way exactly wrong. Not wrong in the way where I'm going to tell you the truth is the opposite. Wrong in the way where I'm going to tell you the truth is weirder. The cup didn't obey gravity. Gravity didn't issue a command. There's no cosmic enforcement agency watching to make sure the cup cooperates. What actually happened is that the cup did the only thing the universe was structured to allow, and those are not the same thing at all. This is the difference that matters. When we talk about human laws, tax law, traffic law, the law that says you can't park here on Wednesdays, those laws are rules that can be broken. They exist precisely because someone might not follow them. They're descriptions of what we want, imposed on systems that could behave otherwise. The law against theft exists because people steal. The law of gravitation is not like that. The law of gravitation is not a rule imposed on the universe. It is a description of what the universe actually does. Every time, without exception, in every place we have ever looked, for everything we have ever tested, it doesn't say you must fall. It says here is what falling looks like, in every case we've ever found. You see the difference? One is a command, the other is a portrait. Let me bring in something to carry this with us. A ball. Nothing fancy, the kind of scuffed rubber ball you might find under a couch somewhere, red, a little flat on one side. You throw it up, it goes up, slows, stops, comes back down. Everybody knows this. Now I want you to think about what it would mean for that ball to break the law. Not just go up faster than expected, not just fall in a funny curve, but actually genuinely violate the physics. What would it look like? It would look like this. The ball goes up and keeps going up and doesn't slow down and disappears. Or it falls sideways. Or it simply stops existing in the middle of the air. Not because of a trick, not because of a hidden string, but because the relationships in the universe that govern how energy behaves, how mass behaves, how space responds to those things, those relationships just didn't apply today to this ball, this one time. And here is why that cannot happen. Not won't, cannot. The laws of physics aren't rules written over top of the universe. They're patterns discovered inside it. Every time we've looked, and I mean really looked, with the most precise instruments human beings have ever constructed, measuring things down to the 22nd decimal place, the patterns hold. Everywhere. Always. Not because someone is enforcing them, but because they seem to be what the universe is. Now here's the plain language pause I promised you. The laws of physics can't be broken because they're not commands. They're descriptions. If something happened that didn't match them, we wouldn't say the laws got broken. We'd say the laws were wrong and we'd go figure out better ones. That's it. That's the whole thing. The law isn't a fence around the universe. It's a map of it. If the map is wrong, you redraw the map. This sounds simple. It is simple. But it completely changes the question. Because now when someone says, can the laws of physics be broken? What they're actually asking is this. Can the universe behave differently from how the universe behaves? And you can hear that the question has sort of eaten itself. And here is where people always feel cheated, and I want to address this directly. Doesn't that mean the laws aren't really laws at all? Doesn't that mean they're just educated guesses? We found a pattern, we called it a law, but maybe tomorrow the ball just flies sideways and we have to update the map. This is the escape route most people grab for at this point in the conversation. And I understand why. If the laws are just descriptions that can change, then they're not really inviolable, and everything I just said dissolves. Okay? Let me show you why this doesn't work. The conservation of energy, energy can't be created or destroyed, only transformed, has been tested more times and more ways than almost any other idea in all of human science. We have tested it in chemical reactions, in nuclear reactions, in particle accelerators, where things are moving at 99.999991% the speed of light. We have watched single photons. We have weighed atoms before and after. The energy always balances. Always. Here is a number for you. The Large Hadron Collider, the machine we built under the French-Swiss border to smash particles together, can detect an energy imbalance of about 1 part in 10 trillion. That is like measuring the weight of Lake Michigan and being off by less than a single raindrop. And in every collision, every one of the hundreds of millions we have recorded, the energy balances. Not approximately. Not usually. Always. If conservation of energy were just a coincidence, just a pattern we happen to notice in the small corner of the universe we've explored, the chance of it holding up at that precision, across that many events, across that range of conditions, would be so absurdly, laughably small that no rational person could take the coincidence explanation seriously. These patterns are not like noticing that the last 20 cars you've seen are blue and guessing the next one might be too. These are patterns that have survived every attempt to break them, every regime of energy, every corner of the cosmos we can observe. And there's a deeper reason they hold, which is one of the most beautiful things I know. In 1915, a mathematician named Noether proved something that should be more famous than it is. She showed that every conservation law in physics, energy, momentum, angular momentum, comes directly from a corresponding symmetry in nature. Conservation of energy doesn't just appear from nowhere. It is a mathematical consequence of the fact that the laws of physics don't change over time. The same rules apply today as applied yesterday as will apply tomorrow. If that's true, then conservation of energy must follow, mathematically, necessarily, not as an observation, as a proof. So when you ask whether you can violate conservation of energy, you're asking whether you can have a universe in which the laws are the same today as yesterday, which we check constantly, and they are. But energy still doesn't conserve. And the answer is you cannot have both. Pick one. The universe has picked. Now let me do the thing I'm supposed to do at this point, which is take the most popular solution and drop it on the floor. The thing people say is this: what about quantum mechanics? Quantum tunneling. Particles that borrow energy. Heisenberg says you can't know both position and momentum exactly, so maybe the bookkeeping is fuzzy enough that something sneaks through, right? No, I say this with genuine regret, because I love quantum mechanics more than almost any other thing in physics, and I would very much like it to be the loophole here. It is not. Quantum tunneling is not energy borrowing. A particle that tunnels through a barrier doesn't temporarily have more energy than it should. It doesn't violate conservation of energy at any moment. What changes in quantum mechanics is our certainty about position and momentum, not the energy budget. The total energy of a quantum system, when you can measure it, is conserved. When you can't measure it precisely, it's because the system is genuinely in a superposition of states, but the expectation value of the energy still obeys the rules. The uncertainty principle is about measurement and about complementary quantities. It is not a receipt for free energy. The total energy in a quantum interaction, when everything is properly accounted for, the particle, the field, the environment it interacts with, balances every time. Quantum mechanics did not weaken the conservation laws. In some ways, it made them more fundamental. The laws come from symmetries, and symmetries live at the bottom of quantum field theory. This is where they live now. They are more secure, not less. So the quantum escape route closes, and now I have to stop and tell you something. Honestly, there is a wall here. A real one. We do not know why the universe has the symmetries it has. We do not know why the laws are the same today as yesterday. We only know that they are, as far as we can tell, everywhere we've looked. We do not know if they were the same in the first fraction of the first second after the universe began. We cannot look there cleanly. We do not know what before the Big Bang even means, or if it means anything, and anyone who tells you they know is offering you confidence they haven't earned. I don't know. Nobody does. This is not a small gap in our understanding. It is a foundational one. The deepest reason the laws hold might be that the universe is at some level we can't fully reach yet, a mathematical object, and mathematical objects don't have the option to violate their own structure. Or it might be something else entirely. We have very good physics and very good reasons to trust it, and we are still standing at the edge of something we cannot see into. I want you to sit with that for a moment, instead of sliding past it. Because here is the thing that I think people actually want when they want to break the laws of physics. They don't really want to violate energy conservation. They want there to be room. They want the universe to be loose enough that anything could happen. They want possibility to be infinite, not merely very large. They want the rules to be negotiable, because if the rules can bend, then the story isn't over. And if the story isn't over, then maybe the part they want most, the part where something changes, something heals, someone comes back, something impossible becomes real, maybe that part is still coming. I understand this completely. I feel it too. But here's what I want to offer instead, because I think it's actually better. The universe has rules. Deep, permanent, absolute rules. Or at least rules that look permanent from where we're standing, which is pretty much the same thing as far as our lives are concerned. The cup falls, the energy balances, the speed of light cannot be crossed. These things are not up for debate, and inside those rules, the universe made you a collection of atoms, no different from the atoms in the air and the floor and the table, following every physical law perfectly, without exception, every moment of every day, and somehow, doing that, becoming a person who wonders whether they can break the rules, who lies awake at night wanting there to be more room, who feels the grief of impossibility and reaches past it. The laws don't have loopholes, but they apparently produce consciousness, which is weirder than any loophole ever could be. They produce the fact that matter arranged itself into something that asks why matter behaves the way it does. They produced in about 4 billion years from a rock near an average star in an average galaxy something that can be bothered by an unanswerable question at 2 in the morning. I don't know what to do with that, I really don't. But it seems important. The freedom is not in breaking the rules. The freedom is in being the thing that the rules assembled, for no obvious reason, out of everything that came before. The ball still falls, the energy still balances, and somewhere in the gap between the law and what the law made, there's a life. You know, someone once asked me if it bothered me that physics leaves no room for free will. I said, I don't know if it does or it doesn't, and neither does anyone else. And I think the honest answer to that is more interesting than either yes or no. That's still the most honest thing I can offer here. The laws hold, as far as we know, everywhere, always. What they permit and what they produce, that's a longer story than any of us have finished reading. The cup falls, the universe doesn't bend. And in the laws that do not break, somehow something built you. Something built the desire to ask. And that desire unanswered and perhaps unanswerable, but alive in every person who ever looked up at the night sky and wondered if the rules had any give in them. That desire is not a failure of physics. It might be its most astonishing output. If the laws of physics have never been broken and never can be, what does it mean that the universe made things that wish they could?